High-content imaging relies on optical microscopy, and one prominent approach is widefield microscopy. There are a number of high-content imaging readers from the mid-range budgets out there that rely on widefield microscopy technology, specifically on fluorescence-based widefield microscopy. Fluorescent-based widefield microscopy uses fluorescent probes to mark samples to generate an image. The image is then obtained by such microscopes, and there's a specific excitation of a specific fluorescence molecule that is acquired. In principle, light is absorbed by a fluorophore and emitted at a longer wavelength. This is called the Stokes shift. And the emitted light then can be viewed by the eye or captured by a camera. Such widefield microscopes are commonly used in biology, and these microscopes in these microscopes, the excitation and detection of a single molecule occur along the same light path. The main advantage of this approach is that the images can be viewed quickly, directly in the ocular of the microscope by your eye, or by cameras that the microscope is equipped with. However, this approach carries a high risk of background fluorescent signals and significant bleed-through from channel to channel. The resolution limit of conventional widefield microscopes is about 250 nanometer in the horizontal direction and about 450 to 700 nanometer in the longitudinal direction. This is called the point spread function, or in short PSF. This is a fixed measure of the scatter of a single point of light diffracted by a microscope. The minimum size of an object that can be resolved by a microscope is defined by this function. Smaller objects appear the same size as the PSF. Objects closer together than the width of this PSF cannot be separated. The PSF is determined by the numerical aperture of your objective lens. For those interested in the physical background of the Rayleigh criterion, there are many videos on YouTube that explain this in detail so much better than I could do.